Anybody have any questions for me? You see there's a new My Math Lab up. And did I put up the paper homework? No, I'm doing it today. So there'll be new paper homework up after today's class. Okay. Is the board well enough lit? Should I up this another notch? There we go. Okay, now it's a little brighter. So we talked about antiderivatives, integrals, right? So remember, an integral is working backwards. We use the words interchangeably, but they aren't really interchangeable. The antiderivative is just a process of going backwards. The integral is what you're doing with the antiderivative. So one of the major things you can do with an integral is that they stand for area. So this is sort of a geometry thing. So if you wanted to find the area under a curve, you use an integral to do it. So take something obvious. Let's say we have the line y equals 2x. And we're going to find the area from x equals 0 to x equals 4. So you would integrate 2x dx. And what you're going to want to do is you're going to want to find that answer at 4 and subtract the answer at 0. Okay? And you symbolize that by putting numbers here and here. And these are called definite integrals. So remember we had the plus c? That's called an indefinite integral, because you don't know what c could be until you do an initial condition. With a definite integral, you don't get a plus c, because what would happen really is you get the c in the first term and the c in the second term, you'd subtract, and the c's would go away. So we'll work this out in a second. So a definite integral gives you an actual number. So what is the antiderivative of 2x? It's x squared, and then what we do is write a little line like that. And that says plug in 4, plug in 0, and subtract. Because if we had done the x squared plus c, and we plugged in 4, we'd get 16 plus c. And if we plugged in 0, we'd get 0 plus c. And the c's would cancel anyway. Because I said, so the indefinite part, the c part no longer matters when you're doing a definite integral. Okay? And it says then that the area under the curve y equals 2x from 0 to 4 is 16. Well, what does y equal 2x look like? Y equals 2x looks like this. Right? That's line y equals 2x. Keeps going. And at x equals 0 with 0. And at x equals 4, this height is 8. This is just the line y equals 2x. So what is this area under here? What's the area of a triangle? And the area of that triangle is 1/2 base times height, which is 16. So you didn't really need it. You don't need to do the high-powered calculus to find the area under a line like that. That's really easy. But of course, you're going to need the calculus if you want to find the area under something messier. And that's what we're going to do today. All right? But just to make sure we get the joke, let's set this up. Okay? So these use something called Riemann sums. So imagine now we just have some curve. Looks like that. And we want to find the area underneath the curve. When I say underneath, I mean between the curve and the x-axis. Well, if we look at the bottom of the curve, of this curve, we know that this area is definitely less than the area under the whole curve, right? And this area if I drew two rectangles, is still less, but it's getting better. Because now I have less error. Okay? To do it again, let's just redraw the curve. If I have one rectangle underneath, I have all of this space unaccounted for. If I draw two rectangles underneath, I have less space that I haven't gotten right. So my error drops. what if I did 4 rectangles underneath it? So if I chop this into 4 rectangles like this, something like that. Now I only have this much error, and so on. So if I do enough rectangles, I'm going to start to get close. Right? Like suppose I did, I don't know, 8 rectangles. So you go, what do you mean by rectangles? What are you talking about? How are we going to figure that out? Right? See, the rectangles, we're starting to fill in that space under the curve. If we did 16 rectangles and 32, so you remember calculus is all about limits. So if we do an infinite number of rectangles, we get exactly the area underneath. So let's think of a process that we can do this that will make sense. So let's pick something nice and easy and figure out the area underneath. Suppose we had just y equals x squared. By the way, the real value of doing this is to understand the intellectual process. So you will have stuff that you do in the business world, and you won't be able to figure out exactly what's going on, but you'll be able to do approximations. And so to understand the approximation process is very important. That you may not actually be able to figure out the right answer, but you may be able to get very, very, very close using techniques like this whole limit process, where you break it up, you take something that's smooth, and you break it up into chunks, and you make the chunks smaller and smaller and more of them, and then eventually you can get a very good approximation. You know, imagine, to digress for a second, if you wanted to find, like, do you know how Archimedes found pi? It's the same process as what we're about to do. He said, well, I have a circle, and this is less than the area of the circle. You don't have to copy this down. That's bigger than the area of the circle. And he said, okay, let's take a circle, let's put a hexagon inside. Whoops. And let's put a hexagon outside. Now we're starting to get closer to the area of the circle. He said, now let's put an octagon inside, an octagon outside. So as you can imagine, as you add more and more sides to the polygon, you get closer and closer to something that looks like a circle. And he found that at some point you got this magic number that just kept showing up, and that's pi. But that you can approximate very well, even about 32-sided polygon is going to get pretty close to a circle. It's not exact, but try drawing one and see how close you get to a circle. 32 sides is a lot. So back to this. So let's see if we can figure out how to get the area. Let's do x squared plus 1. Sorry, that won't affect your notes. Under x squared plus 1. So x squared plus 1 parabola looks like this. We're only going to do in the first quadrant from x equals 0 to x equals 4. Okay? So that's 4, and by the way, that's 17 because 16 plus 1. And what I want to do is I want to approximate the area underneath. So I said, well, let's fill in some of these rectangles. Let's say I want to use 4 rectangles. And this rectangle should be the same width. So each of those rectangles then will have a width of 1, because that whole x-axis is 1. And how could I find the height of the rectangle? Well, the simplest thing to do is use the curve. And what I'm going to do is I'm going to go up the left side of the curve. So I'm going to say when I'm at 0 to 1, I'm going to come up with the height by finding f at 0. So in other words, I'm going to take the width is 1, and the height of this is f at 0. Then the next rectangle, the width again is 1. I'm going from 1 to 2. And now to get the height, I plug 1 into the equation, because I'm going up to here on the curve. So that's going to be f at 1. And then the next one, I go to 2. I go up to the curve. You'll see what I mean by going up to the curve. I'm going to start at the each of these intervals, I'm going to go up the left-hand side. I'm going to pick that coordinate. And where it intersects the curve will be the height of the rectangle. So I'm using from 0 to 1, from 1 to 2, from 2 to 3, and from 3 to 4. And each time I take the left side of the interval. I could do the right side, which we will in a second. And the width of each of these rectangles is 1. To the height of this rectangle, I plug in 2. And then the last one, I'm going to plug in 3. So that's f of 0 is 1. F at 1 is 2. F at 2 is 5. And F at 3 is 10. So you add that up, and you get 18. So we know the area, if I draw those 4 rectangles, well, I can say it's approximately 18. It's bigger than 18, because I have leftover space. I didn't account for this area under here. You go, okay, so it's about 18. Remember, we know exactly how to do it, because we can do that with an integral in a minute. What if I go the other way? What if, notice how each of those rectangles is underneath the curve. It's inscribed in the curve. Let's do it again. Let's do it again, but this time, let's get each of those rectangles by using the right side of the interval. I can use any point in there to create the rectangle, by the way, because height is really just a y value. So let's say this time I get the height by looking from 0 to 1 and saying the base is 1, and the height will come from plugging 1 into the curve. Now let's get the height by plugging in 2, just like before. And now let's plug in 3. And let's plug in 4. Now notice, each of these rectangles goes above the curve. Because if you think about the curve, remember the curve is going up. So when I hit the curve from the left side, I go underneath it. But if I hit the curve from the right side, I go above it. So if I take the interval of the that creates the rectangle, 0 to 1, 1 to 2, 2 to 3, 3 to 4, and I plug in the right-hand value, I end up of the curve. That's because the way the curve is going up. Okay, if the curve is going down, it'll be the other way around. It's not really that important, but let's figure out what these values are. F of 1 is 2. F of 2 is 5. F of 3 is 10. And F of 4 is 17. So that comes out 34. So the first time I guessed that the area was 18, and the second time I guessed that the area was 34. But I know the first one's too small and the second one's too big, so you could average. If you average, you get 26. And remember how I told you how to find the exact area? The exact area is if I just did the integral. So I could do the integral of x squared plus 1 from 0 to 4. That's x cubed over 3 plus x from 0 to 4. That's, let's see, 64 over 3 plus 4. And then remember you plug in 0 and you subtract. So we're doing like 3 concepts at once. So this is 25 and a third. So halfway between 18 and 34 was 26. That's a pretty good guess. So if you just found 4 rectangles underneath, made a guess at the area, found 4 rectangles that go above and made a guess at the area, and average, you already get pretty close. You only had to use 4 rectangles. You know you're not getting it right with 4. What if we used more rectangles? So let's practice this again. and do 8 rectangles. I'll make it a little wider so it's a little easier to see. Okay, so same principle as before. So if we did the left end of the intervals, what are called left-hand rectangles. Well, first of all, each of these rectangles is the same width. Okay? The width of each of these, to get my bad artistry, is a half. How do we come up with a half? Well, the interval from 0 to 4 is 4 units long, and there's going to be 8 rectangles, so 4 over 8 is a half. Okay? It's a half, then 1, and 1 and a half, and 2, and so on. So each of these is a half wide. And I get the height by plugging the left side of each of these intervals into the equation, because that's the y value. The x value is the right, the width is the difference in the x values, and the height is the y value. And I could use the left side, I could use the right side, I could use the middle, I could use a third of the way in, it doesn't really matter. Okay, you just sort of want to be consistent because it makes the math easy. So the width of each of these is a half, and the leftmost rectangle, the left side is f at 0. Then I'd have a half, f at a half, a half, f at 1, a half, f at 3 halves, and so on. So again, each rectangle, you look at the base, and you say it's a half, each base is a half wide, and to get the y value, which gives you the height, I plug in the left side of each of these intervals, each of the divisions on the x-axis. So the last one would be a half wide, and f at 7 halves. You with me so far? Guys, look, no. Some of you have seen this. Depends if you took calc. If you took BC calc, you saw this. Maybe AB. So f of 0 is 1. F of a half is a half squared, a quarter, plus 1 is 5/4. F of 1 is 1 plus 1 is 2. F of 3 halves squared is 9/4, plus 1 is 13/4. Then when we plug in f of 2, 2 squared is 4 plus 1 is 5. I plug in 2 and a half, 5 halves, I get 25/4. So I get 29/4. I plug in 3, I get 10. How many of these have I got so far? 1, 2, 3, 4, 5, 6, 7. Good, last one. And now I've got 3 and a half, which is 7 halves, but squared is 49/4, plus 4 is 53/4. We won't ask you to do something that's painful without a calculator. So you get a half, plus 5/8, plus 1, plus 13/8, plus 5 halves, plus 29/8, plus 5, plus 53/8, which is 18, 47, 90, 100/8. 100/8 is 12 and a half, plus 1 and a half, 4, 9. That's too small. Check again. Now I'm going to make everything eighths. I messed up my arithmetic somewhere. Oh, maybe not. I take it back. No, I didn't. Okay, so that is 19. Which I could have messed up the arithmetic. So it's still low, okay, but it's better than 18. It's a better guess. So, you know, the smart people come along and say, look, just do an infinite number, please. So there's a little fudge involved in that. But let's have you practice one now. Make sure you understand the basic principle. So say I have the curve. Give me a nice easy one. Y equals x squared plus x. And I want to find the area under the curve from x equals 0 to x equals 4 using 4 left-hand rectangles, and then do it again using right-hand rectangles. Okay, take a couple minutes. If you're a little confused, remember each of these rectangles, well, we're going from 0 to 4. We're cutting the interval into 4 units, so each of them is going to have a width of 1. Okay? And then to get the height, you're going to plug in the left side of each of those cuts, each of those intervals, into y. That'll give you the height, and then you multiply them together. So you can plug in 0, 1, 2, and 3 if you're doing the left side. You're going to plug in 1, 2, 3, 4 if you're doing the right side. All right, that's long enough. So what does this look like, first of all? X squared plus x. Well, it kind of looks like the other curves. When x is 1, you're at 1 squared plus 1. When x is 0, you're at 0. And you can go up to about there. That's about 20. So if you want to use left-hand rectangles, which I'll abbreviate LHR, you say, well, I'm cutting this into 4 identical slices, and then I'll get each rectangle by going to the left side of each of those intervals and going up to the curve. So the first one, I just go up to 0. And then you go up to here, and then here, and here. Okay? So the width of each of those will be 1. And I'll do f of 0, f of 1, f of 2, and f of 3. Now you plug those in. F of 0 is 0. F of 1 is 1 plus 1 is 2. F of 2 is 4 plus 2 is 6. And f of 3 is 9 plus 3 is 12. So you should get 20. So well, what if I want to do the right-hand side rectangles? Well, again, they're each 1 wide, but now I get the height of the rectangle by going to the right side of the interval and going up. So I would start here and go across this way, and then like that. Okay? Kind of hard to picture, but the book draws them much better than I do. So each one is 1 wide, and I have f of 1, f of 2, f of 3, and f of 4. So that's 1 times 2 plus 1 times 6. 12 plus 1 times 20. And you get 40. So for example, if this were an exam question or a homework question, we might say, find the area using the left-hand rectangles, using the right-hand rectangles, and then find the actual area. So right now, you say, well, one way I get to the area is 20, the other way I get to the area is 40, so a good guess is 30. It's probably somewhere around 30. So if you want to get the actual area, you would go from 0 to 4, integral of x squared plus x. That is x cubed over 3 plus x squared over 2 from 0 to 4. Plug in 4 and plug in 0. So you get 4 cubed over 3 plus 4 squared over 2 minus 0 cubed over 3 plus 0 cubed over 2, which is just 0, which is 88 thirds, which is not quite 30, because 30 is 90 thirds, right? It's 29 and a third. Pretty close, though. So as I said before, you can make a good guess just by plugging in on each side. So, yes?
In this situation, with the antiderivative, do you still do plus c or no?
You do not do plus c, because as I said, this is what's called a definite integral. Okay? So when you have actual numbers to plug in, you no longer need to use the plus c. Because you get a definite answer. So as I said before, so one thing that people did, because they were very clever, was they said, well, I could just do an infinite number of these and make them infinitesimally thin. We're not going to do that in this class. But when you do, and you play with that, and you make them smaller and smaller, you end up with the integral. That's really what happens. And the math technique isn't that complex, but it's a little bit. And of course, this could be more fun, because we could give you e, or log, or something really painful. But I wouldn't do that to you. And remember what I told you, the area under these is very useful to know. For example, if you were doing total profit or total cost or something like that. So suppose, I don't know how many of you study economics, but you'll see this someplace in the business world, that you know that your marginal cost for manufacturing something was x squared plus x, and we chopped it up into those rectangles. So when you do marginal cost of units, this would be units, and remember marginal cost is the derivative, so this would be cost per unit. And now you've got a bunch of these rectangles that you're adding up. And when you add up the rectangles, you can get an area. And what are the units on these rectangles? It's units on the bottom and cost per unit on the side. I showed you this before. And when you think that you're multiplying them together, you end up with cost. So in other words, if this is the derivative curve, that's the derivative curve, and then these are the number of units, and you put them together, you end up with a total. So integral is a very useful way to find totals of things. So for example, suppose I told you, say, why bother to do all this estimating? I said, you want to understand how the estimating works. One of the things about integrals is you can't integrate everything. You can differentiate pretty much anything, but you cannot integrate pretty much anything. Now in this class, we do very simple functions, but you can rapidly, in the business world, run into functions where you can't. So all you can do is do a good approximation. Suppose that the marginal cost for making jackets at this company is 0.0003x squared minus 0.2x plus 50, where x is the number of jackets, or for the x jacket. And I want to find the total cost of making 400 jackets approximating using 4 right-hand rectangles. So to turn that into a little bit of English, to make sure you can do it, this is your cost equation. You'll get some picture that looks like this. You end up with 400 that you want to estimate the total cost. So you're going to cut this 100, 200, 300, 400. And you use the right side of each interval. Let's see if you can figure that out. By all means, use your calculators. Your phones have a calculator if you didn't know. But I think you did. Let's make sure everybody really understands what I mean by right, left hand of the interval, okay? What you're doing is you're creating rectangles. And each time you create a rectangle, you're using the x-axis for the base, and then you're going up to the curve and using the curve for the height. So where you hit the curve is the height. So for example, at 200 to 300, we use the right-hand side, the right of 200 and 300 is 300. We go up to the curve and across, and that helps us figure out how high our rectangle is. We're going from 100 to 200. I go to 200 and I go across. From 0 to 100, I go to 100 and go across. At 400, I go across. Got the idea? If it was the left side, I would be doing the left-hand value and going across, and I'd end up underneath the curve because these curves are going up. So the width of each of these is 100, and I get the height of the first one by doing f at 100. And then 100, f at 200. You could factor out these hundreds, you know. And 100, f of 300. And 100, f of 400. So the height of each of these is found by plugging into the equation. It's hard to do in my head. Did anybody get an answer? Who wants to stick their neck out and give it a shot? Go ahead.
900.
No, the book says yeah.
49,000.
Okay. Well, somewhere between 900 and 49,000. You got 9,000. Wow. Well, maybe you're correct. The answer key of the book says 12,200. But that doesn't mean that the book is correct, but I can do it really fast. Oh, well, the book's wrong. I get 9,000. So whoever got 9,000, good job. If you got 900, you probably just missed the decimal place. Someone feels bad. All right, so enough of this for today. There is a My Math Lab that's available that's due next week, and I'm sorry to only give you the weekend, but it's a paper homework. I will post this afternoon, and it'll be due next week. Okay. Have a nice weekend.